I would like to express a warm welcome to everybody. This is the third lecture in a series of lectures. I started with a lecture on doing phenomenology in mechanics that relates to grade 10 in Steiner-Waldorf schools. I continued with a lecture on doing phenomenology in electricity that is related to grade 11. And today I am going to talk about doing phenomenology in optics that is related to grade 12 in Steiner-Waldorf schools. My name is Wilfried Sommer. I am a professor for school pedagogy with a focus on phenomenological teaching methods. And I am working as a teacher in the Steiner-Waldorf School of Kassel in physics as well. So my professional focus is where high school and university meet. Okay, let's get started. We are going to dive directly into a phenomenological approach to optics. In Kassel, there lives a wonderful old lady. She was born blind, and she had a surgery to remove her cataract at the age of 48. So she had to learn seeing at the age of 48, and she is able to describe a lot of experience. Usually, all of us experience as a small child. And she describes that after the surgery, she couldn't see anything. For example, when she was in the waiting room of her specialist, she moved her hands and she grasped every part of the chair. And afterwards, she looked at the chair and she needed days to connect what she actually saw with the shape of the chair. And then now at the age of 75, she summed it up in a way that she told me, you never ever really learn seeing. And she practiced 2 hours a day for weeks in order to be able to distinguish different chairs. And she always had to grasp them. And afterwards, she had to look at this direction, and then she had to connect some differences or shapes in her visual field to her experiences she had while moving her arms and grasping the chair. And what she describes is very closely connected to one of the basic tools of a phenomenological approach to optics. And now I would like to introduce one of the basic tools, the tool perspective. And therefore, I'm going to share my camera before you are asked to do a hands-on experiment by yourself. Here I have my document camera, and here I have my 2 hands and 2 fingers, and I just marked 2 points of reference on that fingers. And now I will move 1 finger back and forth, and while doing so, I will try to have always the points of reference on the same height. So you will see the rear finger will become smaller, and you can compare it to the extensions of the front finger. And by going upwards, the finger gets bigger, the right one, and by moving downwards, the finger gets smaller. And through the points of reference, you can really compare it. And in class, you might do it in a way that you will ask the students to look with one eye, the better eye they have, to put two fingers beside one another, two front pointing fingers, and then to move one finger backwards while having the 2 points of reference on the same height. And then they will see that the farther away the finger is, the smaller its extensions in the visual field. That is called perspective, and perspective is one of the basic tools for a phenomenological approach to optics. And now I would like to add something. While you are moving your fingers and the extensions in the visual field change, you are very convinced that the rear finger does not become smaller, and you are very convinced that the front finger doesn't become bigger. Why? Because you have your bodily perception that the extensions of your fingers are not changing. So you have other senses, and you are very convinced that the extensions, the bodily extensions, are preserved. But nevertheless, the extensions in the visual field change. And what you actually derive by bringing together the changing of the extensions in the visual field and the feeling that the bodily extensions are preserved, you are bringing forth, through bringing that together, the idea or the concept of distance. And as a small child, you are doing this frequently in a lot of situations. And through that, you actually start to learn that if something has got smaller extensions in the visual field, it is far further away. So the concept of distance in your seeing is an embodied cognition of bringing together several senses. So looking into the world does not mean just to involve your eyes. If you look at objects, you always involve several senses, you immediately bring them together, and then you have an embodied cognition by formulating this object is 2 meters away with that extensions. You bring already a lot of implicit knowledge into that phrasing. And so seeing is embodied cognition. It's not just rays arriving in your eye, calculating something. In some you are calculating then through the excitation of nerves, something in your brain, and that's it. I would like to make you aware of that the very beginning of looking into the world already is an embodied cognition. And the tool of phenomenology in optics that is called perspective uses this embodied cognition. And now I would like to show you how you can actually use that tool to characterize a lens and especially what's going on in the relation between the focal plane of a lens and the lens itself. I'm going to show a demonstration, and therefore I have to change my camera, and we will meet soon. Here I am, and here I have a lens. The focal distance is 550 centimeters. Here is the focal plane. In the focal plane, I have an object with 7 glass spheres forming the pattern of the number 1. Here we have the object. Here we have the lens. I'm now taking this away for a second. And the experiment you can do with the students is that they have to look through the lens at the object and have to increase the distance to the lens while still looking at the object and observing what's going on. And they will be a little bit insecure what's really going on with the dimensions of the object 1 they see. And therefore you ask them to use their small finger and to fix it on the at the nose, and then to compare what they are actually seeing in different positions. And what they will be observing, I am going to show you now with that camera here. And I will move that camera here from different positions to different positions. And from time to time, I will use my hand like this, like the students. So that is the nose. And that is the point of reference, the dimensions of reference, because you can be convinced that the dimensions of that finger will not change a lot during the 5 minutes of the experiment. Okay, so in order to involve you, I will leave that set up here on my camera, and now I will involve the second camera, and you will have in your small window always this setup, and you can see my acting in the small window, while on the big screen you will actually have what the students will see that is represented by that camera here. You have to wait a minute. Here I am. So this is the eye of the students. And if they move back and forth, they have the impression that the framework of the lens, of course, here changes according to the changes in distance. The farther the distance, the smaller the extensions in the visual field. That is the regular perspective. But they do not have the impression that the perspective of the object 1 changes the same way. And now they have to involve their finger and to look what will be happening. And if I do this here, I fix it, you can see that my little finger obstructs 3 spheres of the object 1. I'm going to increase the distance. It's the same thing here. I'm going to increase the distance. It's the same thing here. So I will do it once again, and please enjoy how the perspective freezes. And if you fix on the object 1, you can experience in yourself that the extensions are preserved. Okay. So far, I will stop involving the camera, and I will proceed to the concept building, and therefore I am going to involve the blackboard here, and now I'm going to zoom the camera a little bit, and I will change the camera, but please wait a minute. Here I have the object, that's the lens. Here's the optical axis. I just wrote down the number of the company Leibold that is connected to this object here. And I also wrote down the number, the article number of the company Leibold, where I actually bought that lens. I have a focal length of 50 centimeters or 500 millimeters here. And that represents my eye with a finger. And this is another position. I have the finger and the eye, and here are further positions. And now I had a situation that my finger here obstructed 3 glass spheres of the eye here, of the number 1 here, 3 glass spheres of the number 1 here, and I was able to see that glass sphere and that glass sphere here. And now I'm going to introduce directions of sight. And I'm just going to take a ruler. And if I just relate to this point here in the middle of the eye, and I have a direction of sight where I was able to look above the finger here through the lens at that glass sphere. And I'm just going to draw this optical pathway and this optical pathway here corresponds to a situation that I was able to see that glass sphere. And in the second position, I of course saw this upper part of the glass sphere in the same direction. This has to be parallel here. Why? Because the distance of the finger and the eye did not change. and I was able to see directly above the finger the glass sphere. So I have to connect it this way. And if I am going to introduce further directions of sight, I have to continue in a way that I do it parallel. And I would be able to continue step by step. What I actually used here is my knowledge that I can introduce an angle here through the relation between my eye and my finger. And then I just used here straight lines to characterize the situation of my observations. And these lines can be denoted in a general way as optical pathways. And these optical pathways at that stage only have the meaning of being geometrical operators that characterize the observations you have in the setup. And now you can start to interpret optical pathways. And I interpreted them as directions of sight here, where you can see it. And of course, you can do it also in another way. You can look at the brightness of that glass sphere here. And if that is very bright and everything is dark, you will see that you have one direction of illumination here in this way. So that if you have the borders here of the framework of the mounting of the lens, you will have shadow lines here in this direction. And if you just introduce here an iris and you reduce the diameter of that lens, you can realize every single optical path here as a shadow border. So I introduce in a phenomenological approach these lines as geometrical operators called optical pathways. Here, first of all, they have the meaning of directions of sight. And if you look at the brightness here, you can just use these lines to characterize the direction of illumination. These lines can have the physical meaning of shadow borders, and you can derive the features of the focal plane of the lens directly with this experiment. And to every spot in the focal plane corresponds one direction of illumination after the plane. That is called a Fourier transformation of the lens. I'm not going to introduce Fourier transformations for the students, but it is a very easy way to connect with a hands-on experiment or demonstration to connect the features of the focal plane with the orientation of the optical pathways. And then, of course, you can continue. In this position, you get it as probably most of you know. You get it without a change of direction at the position of the lens. And then it's very easy to, if you know this, to draw the lines. And now by knowing this, we could continue and do it step by step for every class sphere here. So far, now I will change my position and I will go back to another place. This was a brief example for doing phenomenology in optics, and to start with one tool, perspective, and to use that tool in a combination of demonstration and hands-on experiment in a way that the students can derive the features of a lens with respect to the focal plane by themselves. And you might have noticed that I proceeded in a way that is very typical for Steiner-Waldorf education. I started with the embedded observer's perspective, and I proceeded to look at it from the external. And just to say it once again, very specific in the Steiner-Waldorf approach is to bridge the gap between perceptions and concepts in a way that you start with the embedded observer's perspective, if possible, and then you proceed to the external perspective. And for a phenomenological approach, it's very typical or specific that you start with a particular that contains a universal, and that you try to reveal the universal by working together with the students. And to sum it up, I would like to share now a PowerPoint that is like the conclusion of my presentation. Here, I have a situation similar to the demonstration I just presented. There is a lamp in the focal point of a lens. You look at that lamp through the lens from different positions, 1 to 5. You see that the extension of the lens in your visual field will decrease. But what about the lamp? If I introduce lines of reference here, you will see that the dimensions of the lamp in the visual field do not change, but the dimensions of the lens, of course. If you transform that observation into a concept and you look from the external at it, you have to start from the point that you have a freezing perspective. And if you introduce optical pathways or rays that conceptualize your observations, then they are geometrical operators, and you can derive that each point of the lamp is related to one direction of view. The framework of phenomenology is pretty clear in that example. You start with observations, you describe them, then you introduce a special focus, you try to have a series of experiments. Then you try to bring an order in it. And this order is closely connected to your observations that is specific for that approach. And then you see that every direction of view corresponds to one point of the lamp. You derive geometrical elements from perceptions. And that's a way to bridge the gap between perception and concepts, and the German expression Lebenswelt now is translated here as life world. That is our everyday experience, and you try to connect the life world and the science world in a way that is not alienating. You can use those tools always in looking and seeing, and just to relate it to three lamps being aligned in a row. Here you have the dimension of the first lamp. Here you have dimension lines. The distance from the eye or the camera to the first lamp is 1 meter. The distance between the lamps is 1 meter as well. And here you have half the diameter for the second lamp and a third of the diameter for the third lamp. And you connect, of course, your tangible experience that all the dimensions of the lamps are the same, and you connect it with the changes of the extension in the visual field. And so you realize once again that the perception of objects involves several senses in physics. And so the concept of distance is an embodied cognition. Just to show you another application, especially in Steiner Waldorf schools, where students do surveying in class 10, they know if objects are aligned, the front object obstructs the rear object. It's just showed on the image here, and the concept is presented on the right-hand side. And now I am going to move the table with the two bars from the right to the left. I have a left shift. And now with that left shift, you see that now the relation between the white and the black bar changes while moving the table. Now all three objects are aligned. I'm going to continue the left shift, and the bigger the left shift, the better you can really distinguish the black and the white bar. The obstruction vanishes. So the observation actually is that the nearer the bar, the stronger the shift. I would like to ask you to look once again at the black bar, and you will see that the shift of the black bar is stronger than the shift of the white bar. And of course, all these experiences you start to have already if you hide yourself as a small child behind a tree, and you will see that the shift of objects while moving and the obstruction of objects while moving depends on the distance you have. And that is not only valid for the person that is hiding himself or herself, that is also valid for the person that is looking for the person hiding himself or herself. And so the shifting of objects is not only valid for myself, it is also valid for others. And Hans Jonas put it this way: being an embodied person who can interact with other bodies in space is a prerequisite for viewing. Today, it's called joint attention or joint attentiveness. And the tool I used here in phenomenological optics is called parallax. If you apply parallax to a bar you are looking at through a lens, and you are going to move your eye while looking at the bar, you will see that the bar seen through the lens directly follows your movement. By moving your eye from the left to the right, the bar here always follows your movement. And if you ask, what about the concept here? You have to draw lines here this way, and then you realize that you were able to derive from these optical pathways the features of the focal point. And now, if you have ordered these experiments and your observations, then you can connect to the features of a physical model, especially the model rays of light, the ray model of light. And if you refer it to the ray model of light, you will realize that these geometrical lines, that these geometrical operators are imbued with meaning. They have the potential to make the world bright. And in a philosophical framing, you call that a metaphysical realism. This metaphysical realism imbues those geometrical structures with the potential and the power to produce an appearance. And so the students, having learned geometrical operators now, are also getting or developing an awareness what the difference is between bringing order into experiments or applying a model. And so if you have the impression that a model might explain something, then you realize that it can explain something in a very specific philosophical framing, in the framing of a metaphysical realism. And so they get an awareness of the nature of science. I think that in Steiner Waldorf schools in grade 12, a phenomenological approach to optics opens the chance to sensitize the students for the question, what does it mean to explain something? And now they will learn several approaches for explanation. They can compare it and then can relate it to a philosophical framework. So far, and to end, I would like to show you the reference for my point of departure of my lecture today. That is the book To See or Not to See, where the professor who lives in Kassel and had a cataract and had a surgery at the age of 48, describes what she actually experienced. I would like to say thank you. I would like to express my hope that you will enjoy frequent shared encounters in the demonstrations and the hands-on experiments you will experience with your students, and that you will discover brand new ideas. By the way, students start to build concepts or to derive concepts if they reveal a universal from a particular. Have a good time. Goodbye. Bye-bye.